So for our pyro simulation, we can start with the same setup that we already have. If we go up, we can grab it from our FX Tornado container. So here, this setup with our density, volume rasterize and everything. Let's copy all of these nodes from the set density to the pyro solver and let's Control C. We'll go up and let's paste them in our popnet. And we can see that automatically our popnet is recognized here. So our attribute VOP is already connected. Now, if we look at the result from the volume rasterize, we can probably use a lower voxel size here. Let's try something like 0.1 and we'll use the same for our particle scale. And we'll also use the same settings in our other volume rasterize here as well. 0.1 for both of the voxel size and particle scale. And let's also link this up with our voxel size here. So let's set this to 0.1 and copy parameter, paste relative references here and also paste relative references here as well. And let's take a look at our point velocity setup here and see how our curl noise looks. So if I enable and disable this, we can probably scale this up a little bit more since the particles are moving so fast. Maybe we can use a value of 3 or something like this. Maybe this is too much. Let's use 2 and let's check the swirl size. We might as well increase this as well, or maybe actually a value of 2 was good. Now, we probably also need a little bit more particles. If we look at our volume rasterize for the density, we can see that we kind of have, it's kind of looking quite sparse. So we can just go to our scatter here and let's increase this first value here to 5 and let's see how this will look. So now this is looking more accurate to what I would like to see. So we have a much more filled result now, and let's take a look straight away and see what we get from our pyro solver with all of the default settings. So we can see that in the shape tab here we have a little bit of turbulence. We can keep this on. I'm not sure if we need this, but let's just keep this on for now. And in our sourcing we have our velocity sourced in with the pool method and 10 acceleration strength. So we'll change this in a second, but let's see what the default result will give us. And let's run this for a few frames at least. And we can see that this is quite a, we get quite a bit of resolution here. So this is pretty high quality. Let's maybe go to our setup. And for now, while we are running some tests, we can increase the voxel size to 0.25. And let's run this one more time. And hopefully this will be a little bit faster. So this is the result that we currently have. We can see that we do have indeed a lot of cool features. And I'm overall pretty satisfied with how the smoke behaves. But for this type of explosion, for this type of effect, which is more of an explosion, we would like more of a burst type of feeling. And in order to achieve this, it's better if we go to our sourcing here and set the operation to add. Now, by default, the source scale of 1 might be a little bit too high, but let's see what this will now give us. So when we do this add operation, the velocities will accumulate over time. So this works in this case because we are dissipating the particles. So as I play this particle simulation, we can see that the particles will die out, and this is why we need them to not last as much, because essentially the more our particles are alive, the more our velocities can accumulate, and this will in turn make our pyro simulation faster and faster, and we don't necessarily want that. We just want our pyro simulation to start off fast and then slowly die off as our particles die off as well. So let's go back to our pyro solver and simulate a few more frames. So now as a result, our smoke is pushed way further out. So we can see that this is how it currently looks. And if we were to compare this with our particles, we can see that the smoke is allowed to be pushed outside. And again, this will help us achieve that burst kind of feeling a lot better. Now, we can just scale this down a little bit. Maybe we don't need to introduce as much velocity. So I'll just scale down this source scale here to 0.7. And let's untemplate the points, and we can let's do a file cache actually, and let's save out maybe 100 frames or so and see what we end up with. So let's do our job variable here, and this will be our explosion volume, and let's save to disk. Let's maybe do 1170. So 70 frames should be good for us to decide what other changes need to happen here. So let's take a look, and if we play this, this is what we have. have, and I'm pretty happy with this result. The thing is that after our particles die off, our smoke will just be pushed in the last velocity values that our pyrosimulation picked up from the particles. So when our particles die off at around this part over here, our smoke is just continuously pushed along the direction that it was already going in, and we no longer retain this kind of rotation velocity that we start off with. So if we look at our simulation one more time, we start with our cool rotation here, and after a while we can see that the smoke just sort of spreads out and no longer has this rotation. So to add some of this rotation back, we can create a custom velocity field which we can source in alongside our velocity particles over here. So let's create this custom velocity field. We can start off with a box which will contain our field. So let's increase the uniform scale here by quite a bit. We want to make sure that our box extends to the furthest reaches corners of our simulation. So if I press enter, I can just grab some of these handles here with shift, and I will just scale this up. And again, I'm just wanting to make sure that this box contains almost all of our simulation. So we'll need quite a large box for this, but something like this will be fine. We can adjust this later, and we'll want to create a VDB from this. So let's throw down a VDB node, and let's give this a name straight away. So we already have a name for the velocity here, which is going to be V, created by this volume rasterize. So for this other VDB, we can keep things a little bit. We can really give this any name that we want. So we want to use this velocity field to further spin our particles. So I will just name this volume here spin. The class here can be left as fog volume, but the type I want this to be a vector float, and the vector type will be displacement velocity acceleration. So from this VDB, we can use a VDB activate, and we can plug our box as the second input here, and let's set this type here to reference. So now it's using our box to fill up the VDB. Probably we can use a larger voxel size here. We don't really need to be this high resolution with this velocity volume. Let's maybe set this to 0.2 or maybe even 0.3. So this will make our simulation in turn run faster. This is why we should probably scale up our voxel size here. So after the VDB activate, we can create our velocity volume with a volume VOP. And inside here, we can go ahead and we want to create the same kind of vector that spins around the center axis. And in fact, we can go up and in our popnet here, let's step inside, and in our set V geometry VOP, we can probably grab all of our nodes here. So this cross product over here with the multiply constant, let's grab all of these nodes up until the cross product there, and we don't really need to bring in the multconst node here as well. So let's grab these nodes here, let's Control C, and let's go up, and we can plug them directly in our volume VOP. If we paste them over here, we can grab our position and we can plug this back into our normalize. We don't need this density connection here, we can get rid of this. And if we do Shift S here, let's do one more rundown over the setup. We have our position plugged inside the normalize. This will point away from the center of our scene. We are scaling this down so it's just horizontal, and then we are normalizing this, and we are using a cross product with an up vector to get our spinning motion. So the result from here, we can do a bind export, and this will be exported to our already existing spin volume. Type here, we should set this to 3 floats. And if we go up, we can preview this custom velocity here. Let's maybe drop down in null, and this will be our, let's do spin volume. And to preview this, we can plug this inside a volume trail node, but actually this should be our second input, and we'll need some points to advect along our volume, so we can base this on our box. Let's do from our box over here, we'll do a points from volume, and let's increase this point separation. We can see that this gives us 33 million points, so we probably can lower this by quite a lot. Let's set the point separation here maybe to 1. We can probably also increase the jitter scale here, honestly, and maybe let's do something like this. So we'll plug this in the first input in our volume trail, and here we can clearly see now the spinning vector that we get. So if we want to combine this with our pyro solver, we can also place this in our merge over here. So we have our velocity from the particles to the side here, and now we can just plug in our spin volume as well. And in our pyro solver, we will want to source this in. So in our sources, let's hit plus. So here we'll want to bring in our spin volume. Let's type here spin. The vector, the target field will be vel, the same as above, but the operation, let's set this to pull, and let's use our default acceleration that we always use of 10, and this is also a vector value, so let's set this to vector and turn on direction strength. So now this custom velocity field over here will also be pulling our smoke constantly in this direction. So when we can no longer pick up any of the velocities from our particles, this spin volume will help us maintain this rotation. And we'll see if we need to increase the amplitude of this velocity. So let's go to our volume VOP, and let's also do, before we export this, we might as well do a multiply here, and let's promote the second input, and this will be our strength. So I'll go up and set this to a default of 1. And while we are in this volume VOP, we can also add some noise to this velocity field. So we can go inside and we can grab our 4D setup for the curl noise that we usually do. So let's do here vox for the noise setup, and from this vector to vector 4 we'll plug this inside the curl noise. We can use here analytics simplex noise, and we can just add this on top of our noise, and we can probably add this actually before the multiply. So let's add this here and let's plug our curl noise, and this is what we have. So if we play this animation, we can also see this in our viewport. We can probably scatter less points, so let's increase the point separation here, and maybe we can increase our trail length just so we can hopefully see this better. So if I play this animation now, we can let's go back inside our volume VOP and let's scale down our frequency. Let's maybe reduce the multiplier for both of these values. All right, so let's do something like this. And we can also maybe scale down the amplitude and roughness, but something like this I believe will be fine. So let's go up and let's see how this will now look with our current setup. So let's just do another file cache. I'll use here version 2, and let's save to disk. So if we look at our new simulation, let's see we have almost the same result as earlier. But if we compare version 1 with version 2, we can kind of see that on version 2 we have a lot more, well, not really a lot more, but we do have a little bit more spinning. So this rotation that we just added, as we compare these two results, we can probably also make our smoke last a little bit longer. So in our pyro solver, in the fields tab over here, we can increase or rather decrease the dissipation. Let's try a value of 0.06. And now what we can do is we can just increase the strength of our custom velocity field. So if we go to the second version here, this is what we have. So this is looking pretty good. We can maybe just scale this up by, let's try maybe a factor of 2. So if I go in the volume VOP here, let's just increase this to a value of 2. And let's run another file cache, version 3, and let's save to disk. So let's check out our third version now. And finally, I think we have the winner version here. We do have this continuous spinning and rotation of our volume, and especially if I compare this with the first version, which just pushes out the smoke, after a while our third version is continuously spinning around our center. And obviously, if you want, you can scale this up even more, the strength of our velocity field. And now really we have the best of both worlds. We have our initial burst from our particles, and then we also have this controlled rotation with our velocity field. So I think our pyro simulation is in a fairly good spot, and with the next lesson we can start setting up our final particle simulation. So I will see you there. And we can now do our particle advection. Now in the last lesson, when we saved out this pyro simulation, I forgot to set back our voxel size here to 0.1. So this will be the high quality version of the simulation if we compare this. So I've already saved this in between lessons at 0.1. So this is how my final cache for the Pyro will look like. If we compare this with the second version, we can see that this second version was done at 0.25, and now this new version at 0.1 has a lot more details, and we are going to need some of these details moving forward. So make sure that you recache your simulation at 0.1. So from here we can use this in our particle advection. Let's drop a null, and this will be our out val, and this should be fine. So for our particle simulation, as usual, we want to start with the same setup as our smoke, and we can grab all of these nodes. Let's maybe start with the same geometry. So again, I'll just place my sphere and the transform over here, and I will copy the scatter and the set density attributes, or rather nodes, from here. Let's copy these and let's paste them over here. And for our scatter, we can start at a lower total count here. Let's set this to 5000 for now while we are running our tests. And with our density here, we can also keep this animation. In fact, we can pretty much keep all of these attributes as they are. And let's set this, this is set to pixels. So let's just plug this in our PopNet simulation and see what we get, and also do our advection. So from here, we'll do a pop network and we'll step inside. Let's set this here to all points. And for our birth, in the case for this simulation especially, we are just going to leave the life expectancy of 100. I don't want to delete these particles directly inside this PopNet simulation. I will want to delete them later by using a custom setup. And this is because we have to retime our explosion, and we will slow down our particles by quite a large factor. So when we do our retiming, it's going to be pretty hard to guess what kind of life the particles need to have. So it's easier if we just get rid of the particles ourselves with a simple setup post simulation. With that being said, let's also turn off the guide and let's run our pop advect by volumes. And here we can use the update position method, and let's go ahead and let's go up and grab our velocity volume from over here. We'll copy the path to this node and let's paste this in our subpath. Field name will be val. So if we just run the simulation, this is what we get. So we get a pretty good result right away, I would say, but there's a few things here that need to happen. So first of all, if you've seen the fixed particle stepping video, we can also use this expression here in our pop advect by volumes. We can just scale up the velocity over time. So here we'll do val scale. Let's also zoom in on this. We'll do val scale multiplies equal, and we'll use a fit expression. We'll do in between parentheses at age, and we'll scale this up from 0 to maybe 0.1, and then we'll do from 0 to 1. So over the first 0.1 seconds of when a particle is born, it's going to start with a velocity of 0 and very fast increment this back to 1. And this, hopefully, if we run our simulation now, we should see a lot less of our stepping. Maybe we can scale this up over a duration of 0.2 if we want to improve this stepping error even further. Now, there's still a lot of other adjustments that we need to make here. So first of all, we can get rid of our particles a little bit earlier. I don't really want to spawn them for such a long time as our pyro simulation. So let's go up, and we can also increase our scatter amount just to have a better idea on how our simulation will look like. Let's add another 0 over here. And for our density, let's grab this second keyframe here and let's bring this in. So this will make our particles disappear faster. And let's also increase here. We can go inside and we can just increase our frequency to just introduce a little bit more color in our noise. So I'll just scale up this multiplier here a little bit, so we can go back up, and let's see how this will now work in our simulation. So already we have a lot more interesting features, I would say, and we are getting close to what we want. Now we can see the main problem that we have to fix here is that while I'm okay with how our simulation starts, I'm liking all of these features and this nice roughness that we get. When we advect this at further frames, we really are kind of of compounding this roughness of our simulation. I really want to smooth things out as our simulation progresses, so we get some nice thin wispy trails. So in order to do this, we can run our volume blur setup on our pyro simulation here. So after this file cache, we can do a volume blur. So just like we usually do our magical effects with this setting here, let's use voxel radius. The problem here is that if we increase this voxel radius by too much, we get rid of all of the roughness and it's essentially too smooth. So first of all, I want to link the first value here with our other values as well. So I'll paste relative references, so I only need to change one value. So for example, if I set this to a value of 4 and I run the simulation, let's see what this will give us. We can see that already right from the start we are kind of flattening a lot of our roughness and our detail, but I do like this result more towards the end of our simulation after we have enough particles and enough distance from the center of our scene. I kind of like this result better here with this volume blur, but I liked the earlier result in the beginning where we didn't have any volume blur. So what we can do is we can simply animate this value over time. We can start with a value of 0 over here, and if I hold down Alt and left click, I'll add a keyframe, and maybe over a duration of 50 frames or so, we can scale up our volume blur by quite a bit. We can maybe go, let's try 1060, and let's scale this up all the way to 10. So now over time, our pyro simulation will get progressively smoother, and so this will transfer over to our particle simulation as well. So if we look at our PopNet result now, we can go frame by frame, and we can see right away that in the beginning, we do have all of these nice features and our roughness. And then as the simulation progresses, let's run this for a few more frames, we progressively smooth out this result, and then at the end we don't end up with such a rough look, and we can actually discern more our patterns that are forming from our pyro simulation. So this is what we are looking for, and at frame 1060, where we have our maximum volume blur, this should now allow our particles to travel in a lot more of a smooth direction. So we are avoiding to sort of compound this roughness of our pyro simulation over time. So this is the result that we get, and from here we can right away give these some colors, and we can grab our attribute wrangle with the viewport preview, and from here let's just drop down a color, and let's use this ramp from attribute. We'll set this to CD, and we just want to use as a white color, we'll just use our blue that we keep using. So let's do something like this, and let's go to our explosion, or rather our aura PRT, and inside here I will want to grab this viewport preview, and let's copy this attribute wrangle, and let's go back in our explosion and paste this over here after our color. So now again, this will just allow us to preview better what we are actually going to be rendering. So I can increase the color even more, but something like this will give us a good idea. So this is what we currently have. If we want even smoother results towards the end, we can just increase our keyframe in our volume blur over here. But essentially now we have everything we need to continue with our setup. And from here, really what we want to do is just retime the simulation so it feels more like an explosion. We want our particles to start off super fast and then really quickly slow down until they reach a sort of like a settled speed. And in order to preview our retimed results faster, let's go ahead and scatter less points. We'll go back to 5000. Let's simulate this for a few frames, and we pretty much need to cache around 100 particles or so, because we are going to slow down our particles at around maybe when they get to this point. We don't really need to cache a lot of frames here. So after this PopNet simulation, let's do a retime right away, and here let's set first of all the input frame range. Let's start from our first frame 1001, and we probably need to input around, like I said, 100 frames or so. So let's set the second value here to 1100, and the output frame range, we can keep the default settings for the entire timeline. And if we set our first keyframe for the speed here, we can try something like 2, and we can see the result now. This is roughly the speed on which I would like to start this effect, but then after just a few frames I want to ramp this down by quite a lot. So let's hold down Alt and left click to add a keyframe here and just go further, maybe 30 frames or so up until this point here. And our second keyframe, let's slow this down, let's lower this to maybe 0.2 or something like this. And we will need to, let's shift click this here to open up in our graph, and we'll want this exponential decay here with Control Alt. I'll add another keyframe, and I would like to create this sort of exponential ramp like this. So now if I preview the animation, we get something like this. So this is we kind of have the feel right, but we lose a lot of our expansion here. So we can just push these keyframes further until our simulation gets in the position that we want. And we can see how, as I'm manipulating these keyframes, how this is changing our simulation. So I can just grab my first keyframe here, and essentially when we reach our last keyframe here, I'm judging the rest of how our other keyframes needs to look depending on where our last keyframe ends. So I know I want the simulation to linger when it gets roughly in this state over here. So something like this is actually looking pretty good. And if I play this from the beginning, this is what we have. So now this is looking and also feeling pretty good. We can also just push this in time where our simulation actually needs to start from our retime. So here, let's do a time shift and let's delay this entire simulation. Let's show all objects, and we know we want this to start. Let's maybe just preview the scatter so we're not loading anything. Let's see, if we look at our character, this needs to start roughly at around this point over here. So at 1100, we can just delay this entire simulation by 100. So here we'll do negative 100. And now if we look at we can just preview this from our viewport preview. We have this result. So at around 1100, we are just going to spawn our particles. And let's not forget that we will need to scale these down to their correct scale. So if we do a transform here, we can look at our original transform, which is this scale of 3. So I can use here, we can do 1 divided by 3. And if we look in our camera, this is the result that we get. All right, so let's look at a few frames, and this is what we have. Now, with this uniform scale, or with this effect in general, let's go ahead and Control-Shift-Click to remove the expression, and I can just further manipulate this scale. Let's set this to 0.3, and I can pretty much scale this up if needed, and we can also do some other transforms as well. So maybe I'll just scale this up, and we can preview a few more frames. So I think we need to just scale this up so it's just a little bit bigger than our character when it starts. And I'm mainly looking for this effect to look cool when it gets to around this part. All right, so from over here, I know that probably when the character starts to move and go into the second animation over here, I know that around 1165 or so, I need this effect to be completely faded. So this part over here from around 1140 to 1170 or so, this is where I'm mostly interested in how this effect looks. We see we have some of these particles that are right in front of our camera, so this will cause some issues. So we don't necessarily want this, and we can scale these by the camera position, but we'll do this when we do our rendering in Solaris. So for now, the only other thing that we have left to do here is maybe play around more with our transform properties. We can also maybe just rotate our particles. We can increase the rotation, so maybe we get a cooler pattern if we use this in a different state. So maybe something like this looks a little bit cooler with all of these nice streaks in the back here. And this is what I did in the original project as well. And with a lot of these effects in general, you can play around with the transforms and make it work in your favor. I can also maybe even move this entire particle simulation up a little bit, so maybe I cannot have it intersect that much with our ground. And speaking of which, we can also optimize this if we get rid of some of these particles here. So after this transform, I can drop down a clip and we can just remove all of the particles that we don't see. We'll set this to 0, 1, and 0, and maybe just introduce some padding here on our offset. And this will just optimize things a little bit. We go from 48,000 to 42, so not that much, but it's still worth doing, I would say. And let's go back to our camera. So we pretty much have everything we need. The only thing left here really is to just fade out the particles, and we can just fade them out over time by maybe using the p-scale. So if we do an attribute VOP after our clip, I can rename this one to set p-scale, and let's color this orange. We'll step inside, and we can just scale this over time. So if we do a bind export, we can export this to p-scale, and I can promote the first input here. Let's promote parameter and double click, and this will be our, let's do p-scale value or something like this. So I can go from here, I can set this to 1, and maybe at around 11:25 or so, I will do a keyframe here and just move forward up until frame, let's do 11:75, and let's set this to 0. We can also preview this if we export this to our alpha as well. So if we do a bind export here, we'll set this to alpha. And for our p-scale, we also need our multiply here of 0.01, or actually we can just do a multiply constant, and we know that we already want to set this to 0.01. So here we'll do 0.01, and then we'll further control the p-scale directly in Solaris. So from our viewport preview, we have something like this, which is perfect. And we can just cache these particles up until 11:75. And one more thing to not forget over here, after our retime over here, we also want to compute their velocity. So let's append a trail sop and let's compute velocity and match by ID attribute. So we need velocities on all of these points for rendering. So let's go back up, and after our p-scale here, we can do an attribute delete, and we want to keep our CD, our velocity, and our p-scale. We'll delete non-selected. And for the final count here, I know I need somewhere around a few million. So probably if we just scale up this by 100, we will get around 4.2 million, which should be plenty for this effect. So let's just go back to our scatter here and just add a couple more zeros. And if I run this for just a few frames, let's see what we get. And we start this at 1100. So let's see. All right, so now we can see all of the nice details that we're actually getting from our pyro with more particles. So this is looking pretty good. Maybe we don't really need to bring up this effect this further up. So in our transform here, let's just move this down. Let's just maybe use a 0.2 value on our translate Y. So we have everything we need. Let's run our file cache, and let's actually do this after, or rather before, our set p-scale here. In case we want to modify this later, we can just not include this in our cache. So after this attribute delete, we'll do our file cache. Here we'll say $job, and we can name this one. Let's do explosion PRT. And like I mentioned, we'll save this from 1100 to 1175, which will also be our render frame range. And we can go ahead and let's save to disk. So this will be our explosion particles. And with the next lesson, we can start working on our build up particles. So I will see you there. Now, for our build-up particles, which is going to be this layer, we will want a very, very specific move. So if you can probably guess, we want to use curves as our geometry to base our particle movements on. And we'll use a similar method to how we did our particle trails in the Daemon project with the XYZ, by using the XYZ dist functions to communicate between the particles and curve geometry. But we are going to create this movement directly inside our pop simulation, so it won't be a setup that's mostly working as a post simulation effect. Either way, the first thing that we need here is going to be to create this curve geometry. And over here, we want to create these very curly and organic kind of curves that all converge on the sword of our character. So we want a pretty specific look for our curves, and let's see how we can set this up. Let's head over to Houdini, and we can create a new geocontainer here. This will be our effects build up PRT. We'll color this blue and step inside. So first we want to create some lines that point towards our sword, and then by using some transform logic we can create create all of this curly kind of motion. So we can start by determining where we want our curves and our particle effects to start. And we can start by using a circle geometry. Let's set this to an open arc. Let's set this to ZX plane so it's flat on the ground, and let's increase this uniform scale. This uniform scale here will determine where we want our points to start roughly. Let's increase the divisions here to 50 and let's just scatter some points. So these will become our starting points. Let's disable relax iterations and let's say that we might want to create, let's use maybe 25 points here. We can change this later and we'll want to randomize their position. So we can use a point jitter here and let's maybe hide other objects for now, or let's actually ghost other objects and let's set this to a point display and just increase the point size here in our viewport. So we can see that with our point jitter, actually I'll go up and I'll disable the environment and just focus on our character. So let's go back inside, press F on this and maybe go to one of our, we can see that this is the right view here. So we can increase this jitter maybe for our Y coordinate here. Let's increase this to maybe 2 or maybe 2.2 or something like this. And we'll want to bring all of these points up as well. So we can go back to our circle and just increase this center value here. Let's just use the scroll wheel here and just push these up to maybe 0.6. So something like this will work for our starting points. And actually we do need to bring back our geo environment as well, so we make sure that we are not intersecting with our ground. Let's go forward in time, and this is roughly where we want this effect to start. So now we can better judge how our starting points look, and maybe I'll just increase the total count here. Let's use 30 and we can play around with the seed as well and try to maybe get something that looks a little bit better. Let's set this back to show all objects. We can see that some of these points are now in the ground, so we can grab our circle and push this upwards a little bit more. And actually I will want to decrease the uniform scale here and maybe decrease the overall scale on our point jitter, and let's push these down again and let's maybe change the seed. So I'm not gonna spend too much time right now because we'll create our curves and then we can come back to this so we can better judge what values we need to use here. But something like this will be fine. So the way that we connect these points and create a curve that is going to be on our sword. First of all, we know that if we just duplicate this set of points, we can just connect them through an attribute. So let's create this attribute, and this will become extremely important later. So let's do an attribute wrangle here, and this will be set ID orig as we usually do. Let's use here, we'll set this as an integer attribute. So we'll do I at ID underscore orig equals at ptnum. So now each of these points has a unique ID orig identifier, and again this will be super important later. Let's also color this pale yellow, and from here if we do a transform and I just scale this down to 0, and I can also bring this up, for example, and place this roughly where our sword is, we can do a merge between our points as they are over here and our transform. And of course we can use an add operation and set this to polygons by group, and inside the add attribute, or rather by attribute method here, the attribute name will be our ID underscore orig. Alright, so this is the first step, and now with our transform here we can grab this and move our points around. But really these all of these lines, I don't want them to be converging right into a single point. I want the curves to sort of point towards random spots in our sword, and I would also like them to follow with the sword geometry, because we can see that we have a little bit of animation here. Our character is indeed moving the sword when this effect happens, so I would like all of these curves to, or at least the end points of our curves, I would like them to stick to the sword. So we'll need to reference our character geometry. We can go up and let's go in our geo hero. Let's grab this null and let's copy this inside an object merge back into our chain. We'll do an object merge, paste this over here. we'll need to unpack this. Let's maybe hide other objects for now. So if we do a USD unpack to polygons, we can now go ahead and we can just press S, and in primitive mode, let's select our sword. We can see that the sword has a lot of disconnected parts. So let's just grab this with Shift, hold down Shift and select all of these. And probably I can avoid some of these smaller parts in between. We can see that for the most part, we grabbed our entire blade. So we can press delete and let's delete non-selected. So here we have it, and let's make sure that this is also animated. Perfect. So now in order to get our points from over here to be randomly placed on our sword here, what we can do is we can simply scatter the same amount of points as we have over here. We have 30 points. We can scatter another set of 30 points on our sword, and then we can move this set of points towards our new set of points from over here. So if we drop down a scatter and set this, let's link the total count here, let's copy parameter and let's link this over here. So it's very important that these scatters have the same amount. And let's disable relax iterations. We can choose a different seed here, and let's see if this sticks to our geometry. So we can see that the points don't change position, and this is because the topology doesn't change position, so this is perfect. And now instead of using this transform over here, we can do a blend shape, and we can plug our new scatter as our second input, and we can see that from this position over here, because we have the same number of points, we can just increase this blend value, and now they will move randomly towards our sword. So we can see that this matches this, but we have the same ID or rig attribute from this blend shape, and now in our add operation, we can see that all of our points are pointing towards the blade. So if I also preview this with our object, we can see that now they're no longer converging in one single point, but on random positions on our blade. And the important part here as well is also that this will now follow our blade animation. We can see that as our character starts to move quickly, this will also follow the blade. So it will run throughout this entire simulation. And obviously over here, this is kind of giving us a messy result, but we only really need to simulate this effect up until our character starts moving forward. So at around 1180, our effect will be entirely faded out. So it really doesn't matter what happens on the next frames. So now that we have our initial curves, maybe we can preview this from our camera, and let's take a look. Maybe we can increase this uniform scale a little bit. And like I said, we will probably still come back to this later. We can change the global seed of our scatter as well, but probably more importantly will be the point jitter in our, or rather the seed in our point jitter. Maybe we can increase this also, or actually we can play around with the global seed more so it has a nice spread here. But again, we will need to do the rest of our operations on our curve so we can better judge this effect. So we'll come back to this later. From our add, we will want to now modify our curves. So we will need geometry on our curves. Let's throw down a resample. We can keep this at the default 0.1 value for now, and we will also need our curve view attribute. So let's turn this on and let's throw down an attribute VOP, and this is actually where we'll create most of the look dev for our curves. So we can set the attribute name here. We can do something like transform curves, and let's color this orange. We'll step inside and let's see the base logic of this setup. If we plug the position inside a transform matrix, what I would like to do, let's plug the result back in. What we want to do is randomly rotate our curves on the Y dimension and also our Z dimension. So if I increase this, we can see that all of our particles are rotating. So it's not exactly what we want, but we can scale this rotation by using our curve view attribute, and we can also randomize it by using our ID or rig identifier, which is now transferred over to our primitives. We can go up and we can demonstrate this. If we go to the information here and turn on our ID or rig, we can see we get a random color per each individual value. So our random ID is working. Let's turn this off. So if we step inside, let's first of all do a bind and bring in our curve U, and let's also copy this one and bring in our ID underscore or rig. And let's not forget that this is an integer attribute. So let's set the type here to integer. So first of all, for our curve view, we would like to create a ramp. So let's plug here a ramp parameter, and this will be our ramp curve view. Let's also paste this here, and this will be a spline ramp. And let's first start by trying to modify our Y component here. So the input in this rotation, in this rot slot here, needs to be a vector, but we have for now just a float. So let's do a float to vector, and we'll plug this result in our second input, and let's plug this in our rotation. And if we, let's maybe make some room. If we go up, the ramp that I would like to create is one that looks something like this. So I'll add a point towards the center here and one more towards the ending here. Let's expand this and maybe expand this window, and let's set this to a B-spline. So it's not super noticeable right now, but essentially I would like to keep their ending position and their starting position the same, and just do this entire rotation in between our end and start points. So if I go back inside, if I want to preview this better, we can do a multiply constant just for now. And if I increase this, we can kind of start to see what effect that we'll get. Now, this multiply value over here, this is the one that I would like to randomize per individual curve. So let's get rid of this and use a normal multiply instead. And from our ID or rig, let's do a random. And then from here, let's do a fit range. So let's plug this in our multiply. And for the values here, we can see that as I start to increase the destination mean and the destination max, we get this kind of result. Now, I would like some of these curves to go in a certain direction and rest of the curves to go in the opposite direction. So basically what I want to set here for the destination mean and max, if I set the destination mean to 100, I would like the destination max to be negative 100, so it's in the other direction. And now basically I would like to control these values by just one single parameter. So if I promote the destination mean, let's go ahead and double click this one to expand the window. This will be, let's do our arc rotation or something like this for our label, and the destination max will be the negative version of this. So from here we can just do a negate and we can plug this in our destination max. So now with just one value, let's go up. I can just increase the overall amount and we have this effect. So let's leave this as 100, and we want to do the same setup here for our Y coordinate as well. So this float to vector, really we can place this after our multiply. So let's go ahead and disconnect this, place this over here, and let's make sure that this is pointing to our second value, which is the Y direction, and we'll plug the curve view back into our multiply and the fit as well back into our multiply. So we have the same result as earlier, and now we want the same setup for our third value over here, and we can see as I increase this, we can see that this is the rotation that I'm talking about. So let's set this back to 0, and we'll want the same setup. So, but we would like a different seed for this random value generated on our ID or rig. So I can just copy all of these nodes. Let's duplicate them over here. And for my ID or rig here before the random, let's just do an add constant and just modify this seed value. And for the add constant here, we can just use a random number, something like this, should be fine. We just want to make sure that it's not the same values as our first one. And for our second label here, we can see we have the same name. So we should really avoid this. We can rename this one. We can do destination mean Z underscore Z, and we can do arc rotation. Let's do Z over here, and this will be our Y. And now we will have to multiply this over our same ramp from over here. So let's grab this one and let's do another multiply, plug this over here, move this down, and let's maybe make some more room somehow. We should organize these a little bit, or I can reverse the operation here since this is a multiplication, and I can just bring up my entire setup with our ID randomization and move our curve view and the ramp curve view over here. So now I can multiply this with another set of random values and plug this as our third input. So now this is the result that we get, and again we can just go up and I can increase this arc rotation. I can make this, I can control this any way that I want now, and let's go back up, and maybe we should promote our add operation here before our random. So let's do an add and let's promote our inputs here. This will be seed Z, and let's do the same for our first one here, and we'll do another add and let's promote this one to seed. We'll do seed Y. So now we have all the controls that we need. We can change the seed Z value here, and we can change the seed Y as well until we get something that looks cool for us. And if we look at this through our camera, this is the result that we have. And all of this, let's remember that it's following our sword. And speaking of which, this rotation that we are currently doing is based on world origin. So by default, we are using this 0, 0, 0 coordinate as a pivot, but we want the pivot to be the center of our sword. So from our sword geometry over here, where we have our blast, let's drop down a null so we can point to this, and this will be our out sword geom. And we'll copy this and use an object merge to bring this down below. So let's use an object merge, paste this here. And from our geometry, we can just extract centroid on this. So let's run an extract centroid, and let's run this over detail. So now we have this point in the center of our sword, and it's following the animation as well. So we would like to use this as our pivot now. So we'll plug this in our second input in the attribute VOP. Let's step inside, and from over here, from op input 2, let's do an import point attribute. We want our position, and for the PT now we'll promote this to a constant of 0 because we only have 1 point, and we can now use this as our pivot in our transform. So now all of our rotations will be based around the center of our sword. So this is now a lot more accurate to what we want, especially if this sword, for example, was way off center here or further away from our world origin. And one final operation that I would like to do here, I would also like to scale this down maybe on the Y direction, and we can do this in our transform node here. But if we were to set the scale right now, if I were to reduce this, we are not really getting the expected result, and this is because the order matters here, this transform order. We have currently scale, rotate, translate, but we want our first one to be our rotation. So let's change this to rotate, scale, and translate. And now if I scale this down, we are first rotating everything, and then we are scaling this down. So maybe a value of 0.7 is looking pretty decent, especially if I go look through the camera here, and this is currently the result that we get. And now finally we can go up and we can decide exactly what values we need to use here. We can increase our circle uniform radius if we want this effect to start further away from our character. We can increase this point jitter, we can increase, maybe we can decrease, maybe we can change the seed over here so we have a different distribution, but something like this will be fine. Now as we are doing all of these transform operations, we can see that all of our points, or some of them at least, are being spread out a little bit too much. And another thing that we can do here is we can also control this effect through our ramp, which we haven't talked about. So I can scale this in and out, and we can see the different kind of results that we get. So I will keep this as something fairly basic, but maybe somewhere in the center here I can taper this down, this ramp, to something like this. I think it looks better. So now we can smooth back out our curves if we use another resample. And here, to have a smooth result, we want to treat polygons as subdivision curves. And we also get a nice consistent resolution between our points now, and we can probably decrease the length here. We can maybe introduce more points, but this is roughly the result that we are going to end up with. And we can play around with our seed values here. Maybe we can have something that works. Maybe we can try some different looks here. We can maybe, let's scale down our arc rotate on the Z direction here. All right, so obviously you'll have a different result than me either way, so I'm not gonna spend extra time on all of these values, but something like this will be fine for our next part. And one final thing that I would like to do with this curve geometry is I kind of want to avoid this intersection with the ground, so we can see that some of these go way below our ground, and we can try to flatten them, and we'll have to reference our ground geometry. So we'll go up and we want to bring in our geo environment object here. Let's grab our environment and let's bring this in our container over here. We'll do an object merge, bring this here, and let's unpack USD to polygons. Let's hide the other objects for now. So if I press S, we can select the ground, delete, and delete non-selected. And let's do our flattening inside a different attribute VOP. Let's do another one here. Color this orange, and this will be our, let's do flatten. And we'll want to reference our geometry. So inside, what we can do, if we template the geometry, we can run an intersect node on all of our points. So basically we can make all of our points look straight up, and if they intersect with any of our geometry from the second input, we can just retrieve that position where they intersect and use that as our new position. So inside here, let's drop down an intersect node, and our file, we want to look at our second input. We want the ray origin to be our own position, and for the ray direction, we'll specify this ourselves. Let's set this to a value of, we want to look up, so this should be 0, 1, and 0. But for the intersect, in order to make sure that this will grab the geometry, the length of this vector matters here. So let's go ahead and make sure that we are looking up further than we probably need to. So I'll set this to a value of 100. And now this position that we get over here, this intersected position, we can just use this as our new position. So when we do this, we can see if we go up, and if we, let's maybe just show all objects, we can see now that our flatten will essentially just grab all of our points below our ground and place them directly on the ground. We could have probably done this with a ray SOP as well, but it's worth knowing a little bit about this intersect node either way. Now, obviously, we have quite a harsh transition here. So finally, I would also like to run a smooth. Let's set the filter quality here, or maybe we can keep this as 2, and we can just increase the strength here by quite a bit. Or maybe we can actually set the filter quality to 1, and probably this is too extreme. Let's maybe just reduce this, do something like 75. I think this gives us a good result. And maybe I can bring these points from our flattening further up. So if I modify the geometry from which this is created, our intersect meaning, if we go to this blast node, and if I drop down a transform and just grab all of this ground geometry and move it up slightly with our translate y value, maybe 0.1, this flatten operation will now look at our raised up geometry. So now when we run our smooth, we should probably not have anything colliding with our ground. So if we look through our camera, this is what we currently have, and I can say that this will give us a fairly good result. Let's do a null from here, and this will be our out curves, and we'll need some other attributes on our curves as well, but we'll take a look into that after we set up our particle simulation. So let's start working on that with the next lesson. Now, to start off our particle simulation, we'll need to figure out a source. Now, for the source, I would like all of the trails to start where our curve starts. So we could scatter some geometry by using our initial points from over here, which is essentially the start of our curves if we compare this to the end result. But really, since we are doing some modifications with our attribute VOPs here, and later down the line we might add some noise on top, we might mess up this position, this starting position of our points. So in fact, it's just better to grab the curves as they are and just select the start or the ending points with that group expression node that we kept using. So let's start a new chain from our out curves over here to the right. Let's copy one of our object merges and bring out our curves, and let's hide other objects. So if we do a group expression here, set the group type to points and use the expression first point of primitive, we have luckily we have the point that we needed. Now we know that if this was selecting us our other point. At the end over here, we can use the num_vtx -1 expression to select this other point, but this is the point that we are looking for, and we'll rename this group here to start, and we can do a blast. And let's go ahead and here let's select start, delete non-selected, and set this to points. So now we have our points and they are linked to our curves. So for our sourcing, we can use a simple circle geometry from which we can spawn our points. So if we drop down a circle, let's set this to an open arc, increase the subdivisions, and let's make this way smaller, something like 0.25, and we'll keep the orientation as it is. Let's throw this inside a copy to points and use our blast node as our template points. So we now have this circle copied onto each of our points, but we can see that we don't have any orientation on our points. So we will need a normal attribute on our curves later down the line, and we can also use this normal attribute to orient our circles properly. So over here, after this mode, our last node here should be the polyframe node with our tangent name here set to n, and now our curves will also have this normal along the direction of our curves. So if we go now back to our copy to points, and we can see that they're also oriented right in the direction of our curves. In fact, if I template the curves, we can see that essentially where we have our circles, this is where our particles will start. And the first thing really that we should do is just make them travel along our curves. So after our copy to points, let's create our own scattering first of all. So we'll drop down a scatter, disable relax iterations and max point limit. And let's start maybe with, let's do 10,000 for now, set this back to a pixel display, and use our $FF expression for the seed. So if we plug this inside a pop network, let's go ahead and set the simulation start frame here. Let's look at our curves and also our animation. So show all objects. We will need this effect to start roughly at around, I think, 1100 or so. So somewhere along this point, probably at around 1100, we can start off this effect, and we know we want this to last up until around 1, or rather 1180, 85, or maybe 1180. So something like this. But either way, we should start this at around, let's hit escape, and let's set the start frame here to 1100. And we'll go inside, and we want to use our own points. So we'll set this to all points. And for our life expectancy here, we'll keep this at 100 because we will want to delete the points ourselves based on a certain condition. So if we just play the simulation, we just have our points. We can see that they are following the curves. So our curve geometry is moving. And really, if we are looking at this, or rather our curves, the end, or rather the start points, really shouldn't be moving this much. Let's maybe just look at our curves. And I think that this is happening because of our transform over here. So if I look at the curves from here and bypass this transform, we can see that the starting points here are static, and when we add this will now modify this starting points. And this is probably because we are referencing this pivot as the second input over here. So when we are doing this scaling thing over here, we can see that if I were to set this back to 1, 1, and 1, we don't have our starting points moving. And when we are scaling this down, because this pivot point that we are using over here is grabbing the animation of our sword, the pivot will also move, and in turn will make our starting points move. So what we can do here to fix this is maybe we can just freeze our pivot specifically for our scaling down. So let's grab our extract centroid here and maybe set this back to points, and we can see essentially that this point is moving. And let's just freeze this at somewhere in the middle of our animation at around 1140 or so. We can do a time shift and we can remove the expression so it's frozen at this frame, and we can reference this as our third input. So let's go back inside and let's grab this. Let's make some room over here, and we'll duplicate this import point node and just point this to our third input instead. We'll want to reference the first the same 0 point over here because we only have 1 point, and we can just do our scaling as a separate transform operation. So I'll set this one back to 1, 1, and 1, and let's just do another one, transform matrix. We'll plug this result inside our position, and now this one will be our final position, and this is where I'll do the scaling and use my frozen point as the pivot. So this new import point we'll use as the pivot, and now if I go up and go back to my curves, if I step back inside and scale down our transform here, let's set this back to 0.7. Now hopefully our starting points should no longer be moving. All right, and as we see this, they are stuck in place, but the rest of the operations are the same. So if I go up, hopefully we should see that our circles stay in the same place. If we run our simulation one more time, we can see that really just the orientation is changing a little bit, and this is because of the rotation and the animation, but they are staying in place. So this is what we want. Let's set this back to pixel display. So now the first thing, like I mentioned, the first thing that we like to do is just have our circles, these particles that we are spawning on the circles, follow the direction of our curves. So we will need to reference our curve geometry inside a geometry VOP. Let's grab our out curves node from over here. I'll copy this, step inside, and let's do a geometry VOP. I will color this orange. Let's rename this one to set V because this is essentially what we are going to be doing, setting the velocity. And in the inputs here, I can reference my curve geometry as the first input. We'll set this to SOP, and our SOPF should point to our out curves. So now if let's reset our simulation. If we step inside, we can usually when we do this kind of effect, we can use a PC open and average the position of the closest points our particles will find on our curve geometry. But in this case, we want all of our circles to follow their own respective curves. So we will use an XYZ distance instead. So from op input 1, which is our curve geometry, let's do an XYZ distance. We'll get this from our own position. And let's just plug this inside a primitive wrangle, or rather attribute, as we usually do. All right, so the prim will go into prim, the prim UV will go into the UV, and this should also look at our curve geometry. And for the attribute that we want to grab, this will be our normal. So this is, we'll set this to n, and we can rename this one to grab n. And if we plug this in the velocity, let's see if this works. So if I press play, our particles by default will go in the opposite direction. So let's go ahead and use a negate here to reverse the direction. And hopefully now we should have our initial movement. So we can see that our particles are following the direction that we want. And first of all, let's make our circles a little bit smaller. We will randomize their p-scale as well. So we'll go up, we'll grab our initial circle geometry, and let's set this to maybe 0.1, and let's reset. All right, so probably this is more along the size of what I'm looking for. So let's also randomize the p-scale here. After this blast, we can do an attribute randomize, and let's set this attribute name to p-scale, and we can use the default uniform method here, set the dimensions to 1, and let's do between maybe 0.6 and 1.2. So if we look at this, this will be with our attribute randomize, and maybe we can just increase the scale now to maybe 0.15. We will be able to control the thickness of our trails a little bit post simulation, so it's better to have them slightly larger than what we need them to be, and then we can scale them down if necessary. So if we go to our popnet, let's take a look. So this is good for an initial movement. There's quite a few things that we need to do now. And first off, let's maybe just decrease the scatter amount. Let's maybe remove one of the zeros here and try to run this on a smaller particle count, just so everything loads a little bit faster. But we do have our initial movement, and we can see that when we run this for a few more frames at basically at 1185, our effect breaks, and this is because our curves start doing some kind of weird stuff by following the sword of our character. But we already know that at around 1180 this effect will be entirely faded out, so this is why we have this weird result in our particles as well. But we don't have to worry about what happens at around this part. If I overlay this with the curves, we can see that it's following the curves just fine. We'll have to increase the speed, and we'll do this in a second. But the main thing that we have to fix first of all. Let's maybe go back to just our particles. So the main problem that we have with our current setup is that some of our points will interact with other curves from the circles on which they start. So what we want to achieve is that each curve, or rather each circle that's connected to a curve, we want the particles from that circle to follow only the curve that it belongs to. So currently we can see this clearly here with this circle, and actually I will turn on my ID or rig attribute as well, so we can see some colors for all of our circles. So we can see that over here we have this green value, or maybe let's choose another circle over here. We can see this right away over here with our orange circle, and maybe I'll increase the point count just so we can see this even better. Let's reset the simulation. So here's what happens. We can see that the particles that we are spawning are following a clear direction in this, where essentially we have our curve. We can also maybe template our curve geometry. So we can see it's following this orange one, it's following our curve, but then some of these points that are on the other side, let's maybe untemplate this geometry. These points over here, which are closer to our other curve, are going to start following that curve, and we have this breakup in our simulation. So we want each of our particles to follow a very specific curve. And inside our PubNet, and inside, let's go back inside the geometry VOP, this XYZ dist node has a group which we can use to specify exactly on which geometry we want to look at. But we really don't have a group for our curves, so we have to create a group on our curves, and then we'll also need a string attribute that exists on our points as well, which we can plug inside this group input over here. So if we go up, let's go all the way back to our curves. After our polyframe here, we can, let's drop down an attribute wrangle, and we can create a name attribute using our ID or rig value. So in this attribute wrangle, let's rename this one to set name, color this pale yellow, and here we can say that s at name equals, and if we do the expression I to a, and in between parentheses we can specify our ID or rig value, and we can say the tooltip here says that this converts an integer value to a string, which is what we want. So here we'll do I at ID underscore or rig. So when we do this expression, now we will have an attribute on our points. If I open up the spreadsheet, we can see that on our points we have this ID or rig attribute, and now we also have a name attribute. So these are the same values, but the name attribute is a string. So this is what's important here, and I can make this even more obvious if I append a word here in front. We can do in between quotations, we can say piece underscore and do another double quotes like this, and then we just do plus this I to a expression. So now when we evaluate this line, we end up with this name attribute which has this piece prefix, and then we have our value. So this is how fractures are usually set up, and this is also why I use this piece as our prefix. So we have this piece 0 all the way up to piece 29, so we have 30 curves. So now if we reset our simulation, I can go to our PubNet. Let's remember that this will be inherited on our circle geometry. So if I reset the simulation, we will have the same result, but now if I go to the information here, we also have a name attribute. We can see this over here. It's a string, and it has 30 different values corresponding to our 30 curves. And now we need to create groups based on this name attribute. So we have a option here. After our attribute wrangle, we can use the sop group from name, and if we append this here, this will do exactly what it says. It's going to take our name attribute and create groups based on this name attribute. Now, the name attribute here is name, but the class here, we can see that this is set to primitive, which is what we need. So the XYZ dist node will look for a primitive group. But currently our name attribute is on the points, so here we will do an attribute promote, after our attribute wrangle, and we'll go from point to primitive and we'll select our name attribute. So now in our groups from name, if you go to the information, we have 30 primitive groups, each corresponding with our name attribute. Now the problem is that with this attribute promote, we also need to uncheck delete original, so we need this name attribute to exist on our points as well. So now we have, if we go to our final curve setup here, we have all of our primitive groups, and we also have this name attribute, which is the same value. So now if we go back to our PopNet simulation, if we reset our simulation, we will still have the same result. But if we go inside and inside our geometry VOP, in our group over here, we can bring in our name attribute with a bind. So this will be a string type, and the name here will be name. So we can plug this in our group, and now we can see that this is the result that we currently have. We can check out this messy part over here, and in fact we can go up. So when we reset our simulation, we should no longer see this this mess over here, and let's see and give this a second. So now we can see that everything is fixed, and if we just simulate this for a few more frames, let's maybe actually go back to our 1000 scatter here and reset simulation, so it's just loading a little bit faster. Now we can see that all of our points will just look at the curve that they belong to, and we no longer have to worry about our points latching onto different curves, and now we'll have a nice predictable result. And sometimes we do want our points to be able to latch onto different curves, as sometimes that creates more variety and it creates a more organic kind of result. But usually when we do that setup, it's better to use a PC open instead of the XYZ distance instead, because the PC open allows us to filter an average position, so it will create an overall smoother transition if indeed our points start to latch onto other curves. But in this case, we want them to stick entirely to our curves, because we are going to do some post-simulation operations as well. And for those operations, we will need to communicate again with our curve geometry. So we will want all of our points to just look at a single curve. So hopefully this will make sense more as we continue with our setup. But this will essentially be the base. And one more thing, since we have this connection between our particles and our curves, we can also add some noise to our curves as well. And we can do this after our smooth over here. We can do an attribute VOP, and let's rename this one to add noise. Let's color this orange, and we can step inside, and we want to use a curl noise. So let's remove our global node here and do our setup here for our 4D noise. So I'll plug this inside a curl noise, and let's add this on top of our position. So we'll drag the position, place down an add node, and let's plug this here, and we'll want to use simplex noise. Let's increase our step size, and let's reduce our roughness. And now I can probably decrease the multiplier on our position and also probably our time as well. Let's see how this speed will animate. So let's preview a few frames. Probably I can make this even lower, and I'll decrease the amplitude. Now we'll link the amplitude to our curve view in a second, but let's try to find some base values to work with here. I think this is fine. So we want our ends and our starting points to stay in the same position. So we'll do a bind and bring in the curve U attribute. Let's do a ramp here, and let's rename this one to ramp curve U, set this to a spline ramp, and we'll plug this as our amplitude. And we'll also need a multiplier over this. So let's promote the second input here, and this will be, we can name this label to amp. And now if I go up, I can add just 1 point or a couple of points in the middle here. So our first and last point are 0, and I'll set this to a B-spline, and now I can just increase the amplitude, and we can see that this will just affect the curves in the middle. So if I play this animation now, we can maybe go back and I can introduce more frequency. Let's do something like this, maybe introduce more animation as well. So if I play this, Let's maybe go back a few frames, and something like this will be fine. So this will just help us. Maybe I'll just introduce more animation here. So this will just help introduce a little bit more variation. And especially if we were to do something like this without the group setup on our XYZ disk, because our curves are changing the position over time. For example, maybe they will get to a certain point where this curve is closer to this curve. So now some of the points from over here will latch onto this curve and it will create a more messy result. So like I mentioned, sometimes you want this and it's best to use a PC Open in that case. But we want these to stick exactly to our curves. So now if I go up and reset our simulation, we should also see this noise animation on our curves being transferred over to our simulation. So if I play this animation now, we should already have a more organic and natural result. We can see that if I run the simulation for a second, we can kind of see that some of these curves are moving a little bit as well. They're changing the position. So just introducing a little bit of variation, but most of this movement will be controlled through our geometry VOP inside our PubNet. So with the next lesson, we can take a look into how we can further add to this initial velocity and really create a cool simulation. So I will see you with the next lesson.